Thank you very much for the kind introduction and a very warm welcome also from my side to this webinar on the solid phase microextraction technique. A question at the very beginning. How advantageous would it be to analyze volatiles and semi-volatiles with no sample prep on one instrument only, and this at low cost for high sample throughput? We will find answers during this webinar. SPME, or we call it SPME in our lab jargon, is not new. It was in 1990 when Catherine Arthur and Janusz Pawlicin used coated fused silica fibers for the extraction and desorption in a GC. The basic procedure is still the same today, but a lot of development happened. We will move on to some fundamentals of SPME fibers and the SPME arrow, and also see how automated methods are easily set up on the pulse system. Then we move on to the application side. Headspace or direct immersion SPME, quantitation and derivatization are subjects to shed some light on. Besides GC, also LC and direct MS couplings are in use as well. We then will dive a bit deeper into the optimization of SPME analysis with a typical application. It is about flavors, but in this case about the nasty flavors from water. We will see a few easy but necessary steps to establish an optimized SPME method. As the name says, SPME lives from the solid phases, the sorbent materials of the coating. Here we see the various sorbent materials in use for analytes of high and low polarity and also of different volatility. PDMS, for instance, covers a range of VOCs and semi-volatiles with a different coating thickness. PDMS is also present as the glue with more polar sorbents like divinylbenzene, DVB, or the polyacrylate. The big gray arrow in the back is of particular importance. We call it the triple phase. The coating is with DVB, a porous carbon material, and again PDMS. This coating is very popular to cover a wide range of analytes with different polarity and mid to high volatility in one method. We will see this type of mixed sorbent material again with the off-flavor application. Here's the classical SPME fiber. The fibers are available with all standard sorbent materials with coatings from 7 to 100 micrometer thickness. The fibers are made from fused silica or an elastic nickel titanium alloy. Diameters of the fibers compared to syringe needles with 23 or 24 gauge. For the best peak shape during desorption, a very narrow inlet liner of only 0.8 mm is recommended. On the right side, we see the pulse SPME tool. The SPME fiber devices are pre-mounted and look like a syringe, and they are inserted into this tool also like a syringe. The plunger heads are color-coded to distinguish the coatings. A new development came a few years ago with the SPME arrow. This is a big step ahead in SPME. The arrows allow a larger sorbent surface and also a higher sorbent volume, which translates directly into higher sensitivities. On top of that, the arrow is more robust and is unbreakable. As the name arrow says, another big difference for daily operation is the sharp arrow tip you see here in the center. It goes smoothly even through thick septa with even low force than the fiber rods. In contrast, the fiber rod is an open tube, which is known to be prone for septum coring. With the arrow, septum coring does not happen anymore, and chromatograms are free from the silicon ghost peaks. The SPME arrows come with the same standard sorbent materials, but the coating is thicker. It ranges from 100 to even 250 micrometer. Also, we see here the plunger heads are color-coded for the sorbent material. The arrows are available in the standard 1.1 or also in 1.5 millimeter diameter. For the best peak shape during desorption, also here, narrow GC inlet liners, in this case of 1.3 or 1.7 millimeter ID, are recommended. The GC septum nuts need to be adapted accordingly. For thorough cleaning, the arrows can be rinsed with solvents. This is recommended in particular for direct immersion experiments. An important step for process safety in SPME was achieved with the introduction of the smart data chip in the plunger head. The installed SPME type is then copied to the PAL system. This sets the operation parameter for the installed fiber or arrow immediately without any manual interference, and this avoids accidental misuse. During the use of the fiber or the arrow, some operation parameters are recorded to track the usage and provide a measure for preventive maintenance. These are the set temperatures, number of samples, and also the time of usage. There's also an expiry date available. On top of that, individual user parameters can be edited and are used by the PAL system, for instance, to monitor the maximum allowed number of samples. The status then is monitored in a traffic light bar on the handheld controller or in the virtual terminal. How to set up SPME methods on the PAL system? This is fairly easy. The PAL method composer allows us a quick and easy setup of any kind of workflow. We see the method composer here on the bottom right. It is used to pull the desired activities as a sequence into the center of the screen. The default parameters can be then adjusted as necessary. For the SPME analysis, there's already a complete SPME workflow prepared for from the extraction to injection, as we see it here in blue. It uses the overlapping mode for the incubation and the extraction during a GC run. It sets the agitator temperature, it takes the SPME tool, fiber or arrow tool, and moves the sample vial into the agitator. Here we wait for the incubation time. Then there is a precondition of the fiber or the arrow at the recommended temperature of the sorbent phase, which is about 60 seconds. For the arrow, we move the vial into the heat exer unit. We then penetrate the sample vial with a SPME tool, extract the volatiles of the sample while shaking. After extraction, the SPME tool is moved to the GC injector, and there it is desorbed, either the SPME fiber or the arrow, at recommended temperatures for 60 to 120 seconds. Then, after the desorption during the GC run has started, there is a reconditioning again, and the PAL system is ready for the next sample. Which options do we have for sampling with SPME? These are the extraction from the sample headspace or the direct immersion into an aqueous sample. For headspace SPME, we keep the sorbent phase in the sample headspace, as we see it here on the right. It separates the VOCs completely from the solutes, which is a perfect sample preparation procedure. Aqueous samples are incubated at 60 to maximum at 80 degrees C, while we constantly shaking the vial. This is also useful for solid samples. Here the shaking is shut off. Typically this is an equilibrium method. We have an equilibrium from the sample to the headspace, but there is also a second equilibrium between the headspace and the fiber or the arrow phase, which is in use. For the direct immersion SPME, the phase is immersed directly into the aqueous sample. We see it here on the right side. This collects the semi-volatiles and the solutes from the sample. Heavy shaking is here important to avoid the depletion of the liquid layer around the aero sorbent material. This uses the heat exchanger. The heat exchanger here on the right keeps the top of the vial and also the arrow in position while it's shaking the bottom of the vial in this flower pattern. So this gives an intense turbulence around the arrow phase and maximizes the extraction of these semi-volatiles or solutes from the aqueous media. Quantification is one of the main tasks for SPME operation. So how to do quantification? We look here at the extraction time profile of a SPME extraction. 3 phases can be distinguished here. One has a steep rise. This is almost linear at the beginning. And in 2, there is then a slower increase of the intensity. Finally, in 3, there is a continuous approximation to a maximum value, but we do not need to wait that long. Extractions are typically stopped after the phase 1. This is what we call a non-exhaustive extraction. Longer extraction time, you see here from the graph, cost time, and they do not increase the response significantly. Important is here the time and also the temperature of incubation must be absolutely reproducible for the sample and also for the calibration. This is the task of the PAL system that can do that very well. It is automated and can control these parameters with great precision. For standardization, internal standards or even labeled internal standards are in use. This here is an example. The SPME analysis here is for the halogenated VOCs, which have very different distribution coefficients into the headspace. 4 milliliter of water were incubated here at 50 degrees C with an addition of sodium chloride. We see the response for these 4 compounds with an increasing extraction time up to 2 hours. After 30 minutes, already there is a good sensitivity reached. Longer extraction times would not improve the response very much. In particular, you see this for the 2 compounds of the lower intensity. So what is the analytical difference collecting extracts between the SPME fiber and the SPME arrow? Again, we look here at the extraction time profile. First of all the SPME fiber methods we have can be used with the arrow as well, but there is more to talk about. With the higher surface and sorbent volume, the raise of the arrow curve is significantly steeper and it goes to higher values faster. If we need the same analyte response or peak intensity as with the fiber, the extraction time can be much shorter. So we can get a significantly higher sample throughput then. This is the number 1 case in this graph. The number 2 shows the effect if we keep the same extraction time as with the fiber, then the response will be better. The peaks will be higher. For a quantification, this is beneficial as we get an improved precision. In practice, a combination of both is used with the arrow, shorter extraction times for higher signal intensity. Polar compounds we extract with SPME often need a derivatization for GC-MS analysis. This is mostly true for the direct immersion analysis if it is not followed by an LC-MS analysis. For derivatization, we need an extra vial with a derivatization agent. This derivatization vial is put into a reserved position of the agitator, and it is kept at constant temperature, for instance at 60 degrees C. This allows us a pre, post, or a pre and post derivatization, which is very often described in the literature. After the extraction from the sample, the SPME arrow moves here into the MSTFA vial in the agitator, and it is kept here for the desired derivatization time. After that, finally the arrow is desorbed in the GC injector as usual. On the right we see a widely used analysis done in breweries for the analysis of stale aldehydes in beer. After a post-extraction derivatization with MSTFA, the aldehydes give a nice chromatogram we see here for quantitation. This is a pretty quick and automated analysis without much sample preparation. We leave GC and GC-MS for a moment and look at other ways to analyze. For sure, polar compounds go well with LC or LC-MS. This requires a liquid desorption, typically done in microvials with the LC mobile phase. The SPME phase should immerse completely into the solvent. Then, after a tool change, this extract then is injected as regular into LC valves that are installed on the PAL rail. Applications here cover, for instance, phthalates, pesticides, or pharmaceuticals from water samples. Recently, also direct MS analysis using accurate mass or MS for targeted analysis are in use. This allows a high sample throughput as the time-consuming chromatography is avoided. DART MS, SIFT MS, Secret MS are the commercial solutions for direct MS SPME. This mass spectrum here shows a pesticide standard with the individual molecular ions of the analytes. This takes less than a minute of MS analysis time only. Also VOC analysis in different areas, from food to breath gas, are described. We now take a closer look into a real-life experiment for the optimization of the SPME analysis for off-flavor compounds from water. Important for sure the choice of sorbent phase. Here we used a triple phase of DVB, carbon, and PDMS for the wide range of compounds which have a very wide different chemical nature. We then see the effect of the extraction temperature and choose the most appropriate extraction time. A salt addition is important here, and also the consideration of a suitable pH for the sample. Last not least, independent from the sampling processes, the correct desorption in the GC injector is responsible then for the nice chromatograms we get. At first, we check the extraction temperature. We look at the chromatogram from two different angles. How do the early eluters behave? Usually these are the VOCs. And then the look at the end of the chromatogram and see the effect on the late eluting compounds. Usually these are the SVOC compounds. Here we checked a temperature range of 30 to 70 degrees. And if we look at the early eluters, a good response already was achieved at 40 degrees C. Increasing the extraction temperature above 40 degrees C shows that the response of the VOCs is decreasing. If we look at the late eluters, which we have here after 20 minutes retention time, it shows that the extraction efficiency is increasing with the increase of the temperature. But if we look at the chromatogram at 40 degrees, we see that there's already sufficient intensity achieved. It's only that if we do a targeted analysis for the SVOCs, we would get more potential for more sensitivity here by increasing the extraction temperature. So analyzing a wide range of polarities and molecular weights requires us to find a suitable compromise for the incubation temperature and also for the extraction temperature. With regard to the extraction time, we look at these two sites as well. Here we tried different extraction times from 10 to 60 minutes. If we look at the early eluters, an optimum here is already reached after 30 minutes. Longer extraction times, as we discussed this already in the beginning, do not change the response much. But for the late eluters, after 20 minutes retention time, the extraction efficiency increased significantly with the extraction time. So looking at the intensity, we get a extraction time of 30 minutes was selected for the standard method later. This fits well also to the intensity we get for the late eluters, and longer extraction times would significantly reduce the sample throughput, but no analytical benefit. A common measure in SPME, especially for aqueous samples, is a salt addition, and if required, also an adjustment of the sample pH value. Here we added about 2 grams of sodium chloride to the vials before adding the sample water. The salting out effect, as we call it, increases the ionic strength of the sample, and it affects the neutral polar and also the higher molecular weight compounds in headspace SPME. We use sodium and ammonium chlorides or sulfates, typically in a saturated solution. In a similar way, the pH addresses the dissociation of analytes. At low pH, analytes with carboxyl or hydroxyl groups like acids or phenols are detected with better response. In this experiment, we used a pH 2 and we achieve a 2-fold increase then for dichlorophenol and about a 4-fold response increase for vanillin. A similar situation is seen with high pH values. For this purpose, we added sodium hydroxide to the sample to get a pH of about 13. Basic analytes like those with amino groups show an improved response, or they get detected at all. Dicyclohexylamine and ethylaniline only show a low response at neutral pH in the sample, and here they get significantly better detected at a pH of 13. Besides the measures for a improved extraction, we also have to look closer to the desorption in the GC injector, as this makes the chromatograms. All the GC injectors are different. They are different in length and in particular with their temperature distribution in the liner. Usually the temperature at the center or at the lower parts of the liner is high and it is closer to the set point. So a desorption deeper into the inlet is more efficient. What we checked here is an injection depth of 40 to 65 millimeter. And we see how this affects the peak shape and for sure then also the sensitivity of the peaks we can detect. It affects both in A, the low boiling compounds, the VOCs, early eluting, and in B, the higher boiling, the late eluting compounds. So this experiment was done on an Agilent MMI injector, and the final inlet depth we choose here is 65 millimeters, which gave us almost some nice symmetrical peaks. So in conclusion, the SPME penetration depth needs to be optimized on the pulse system for your GC inlet to get the best sensitivity and peak shape. This is easy. It is just one parameter in the whole workflow. Finally, when all discussed parameters are optimal in place, we get such nice and also sensitive chromatograms. This quality for sure is needed for a solid calibration and quantitation. We get a good linear calibration here in the range of 1 nanogram per liter to 500 nanogram per liter with very good precision for all of the order compounds. Also, the reproducibility shows very good RSDs of less than 5 or 10% for such compounds in this setup. The only exceptions are the acidic phenol compounds. We did not do a derivatization for these compounds here. We see in this list all the compounds from the light VOCs. This is the first one is propane thiol at 2.9 minutes in retention time, down to the late eluting compounds with benzyl benzoate at 24 minutes retention time. In conclusion, about using SPME for your samples, it is truly a green analytical method. SPME works completely solventless. It is fully automated on the pulse system and it does not require any other sample preparation. SPME is fast, it is quantitative, and it is very reproducible. VOCs typically are collected by headspace SPME. SVOCs and solutes we do by immersion sampling here. SPME methods can be selective, but also, as we've seen, are general. A wide variety of available sorbent phases are available for that. With regard to analysis technique, SPME is used for GCMS for sure. It is also used for LCMS. And it is also used more and more for direct MS applications because this is so fast. With that, I thank you very much for joining our SPME webinar. I would be very glad to answer any of your questions with regard to SPME analysis of your samples. Thank you very much.